As molecules get bigger, their shape gets more and more complicated, and this leads to several other considerations that we will have to take account of. One of these is structural strain, so we'll spend this video learning a little bit about that. Our learning goals include how we build extended, complex structures by connecting centers that have defined local geometries, and then the origins and nature that strain can occur in larger molecules. So you may recall this chart where we talked about the different structures, the building blocks that we would use to build, for example, Lewis structures or structural diagrams of molecules. Well, now that we know something about the local shapes of these, we can transform this table to now talk about the shapes of the primary and secondary structures that arise from carbon, nitrogen, and oxygen bonding things. So it's connecting these shapes together now that will guide what the local shape around different parts of a molecule are. Now, when we connect these together, it's going to lead to more and more complex structures. So let's just take for an example, let's connect a bunch of tetrahedral carbon building blocks together to create a longer chain type molecule. So you can see that each time we add a carbon, it's preserving the local tetrahedral structure of the bonds around it while extending this length of a chain as a 5-carbon chain. So each carbon has a 3-dimensional structure around it, and the chain does not all necessarily lie in the same plane. Now this is how it would look in a 3D model simulation of it, and this is how we might draw it as a bond line diagram. You can see all 3 of these representations are describing the same molecule. So when you see a bond line diagram like the one on the right, you should be thinking of the pictures that you see on the left, because the molecule is really a lot more complicated, a lot more nuanced, if you will, than a simple bond line diagram. Now, structural strain comes about from a couple of different combinations. We're going to look first at how molecular shape is defined by those contributions, and then we'll see how that leads to structural strain. First of all, there's the local environment that defines molecular shape, and then there's a more global environment that defines its shape. Local environment is the number of electron clouds around the central atom. If there are non-bonding electrons attached to that atom, should it form any pi bonds, that also influences the shape. And the polarity of sigma bonds influences that shape. These last 4 are all really VSEPR model projections, as well as small variations on that. The global environment is what leads to repulsive interactions with nearby atoms. That is, nearby and not connected to an atom with a bond, but nearby because the structure of the molecule brings it nearby. It also can be constrained by things like ring systems. If we connect our atoms together in a ring, and we'll talk about that more in Module 5, this also can provide some constraints that affect the shape of the molecule. These are the things that ultimately lead to strain energy. So all the things we've been talking about before with the VSEPR model, those are affected by the electrostatic attraction repulsions that go on between bonds. The global environment is what gives rise to the strain energy. So it's not something that's only going to come about when we have a larger, more complex molecule. All right, so what do these look like? Steric interactions are the most common form of strain that arises, and steric is just a fancy way of saying that atoms get in each other's way. So I want you to consider 2 atoms bonded to neighboring carbons. So here's what that might look like as a cartoon. All right, if those 2 atoms are large enough, maybe they're bromine atoms or iodine atoms, so they're very large, they get in each other's way, and because they get in each other's way, they tend to push the molecule so that they have more space. So they try to engage in a way that will be able to separate them from one another. All right, I've drawn this as van der Waals radius hard spheres. Van der Waals radius is just a formal designation that says this is about as close as an atom will allow other atoms to get to it. That forms the van der Waals radius. And so we also call that a hard sphere radius because it's like having a hard ball around that atom, and no other atoms can come closer than that. Now, if we put this on a larger scale, we might consider a molecule that's sort of based on ethane, where you've got 2 carbons bonded to each other, and each of them is attached to some other things, and the other things that they're attached to are all getting in each other's way. This is what gives rise to steric interaction or steric strain. All right, so what can happen in this case is that steric strain distorts those bond angles. So for example, the ones that are indicated there involving the two central carbons, they can be pushed outward in order for those atoms to get farther apart from one another. Atomic size can be very significant in this, and you should know that even the hydrogen atoms, which are very small on an alkane chain, they're large enough to cause a steric strain. So for example, the molecule we were looking at earlier, if we were to actually measure those central bond angles, they're all larger than 109.5. Ordinarily, VSEPR model would suggest that all of these are tetrahedral centers. They should have 109.5 degree bond angles, but they're all larger. And they're larger because there are these steric interactions between hydrogens on neighboring carbons. All right, we're going to explore this in a little bit more detail in the upcoming lessons, but this gives you a little bit of an introductory look at what causes steric strain and how it changes the positions and shape of a molecule.